So hi, I'm Zach from AMI. We're going to be discussing enabling advanced NVMe features through UEFI. So why don't I just start by asking the question, does anybody here not know what NVMe is? Okay, so we won't spend a lot of time going into too much detail on what NVMe is, but some basic information. Traditionally, disk drives existed on multiple different buses. IDE, AHCI, SAS, fiber channel, many different types of ways. The disks being slower than their parent bus meant that it wasn't a problem for the parent bus. They could continue to invent faster parent buses as long as the disks were still slower. But the problem was eventually SSDs really started to outpace their parent bus architectures. So they needed to start to put them closer to the actual hardware or the fastest buses, which PCI Express is pretty much where NVMe plugs in. NVMe is also a specification. Similar to UEFI, there's a standards body behind it, an industry group, mainly hardware vendors. There's 3 different specs up on their website. You've got the NVMe Express 1.3 is the latest one. That's the main one that's related to UEFI. There's 2 other ones, NVMe over Fabrics and NVMe management interfaces, but those don't really apply in the firmware space as much. And like I said, similar to UEFI, there is a standards body, but they also host test events, their own plug fests. So I would say some of the hardware vendors of NVMe that are here probably also attend those events. So just a quick comparison with AHCI. The latency you can see is about just under half. The multi-core support is limited in AHCI, but full support in NVMe. The 4 kilobyte efficiency is not as capable under AHCI as it under NVMe. They've done a lot of optimizations for quick access and low latency on NVMe hardware. So NVMe, it's been around for a little while, but it really started to become popular a few years ago. And it's now become the primary boot media for pretty much all high-end systems, and servers especially, even low-end systems, a lot of them are using NVMe. So you've got servers, workstations, desktops, even laptops are coming with NVMe drives now, just for their increased speed efficiency. UEFI was also quick to adopt this NVMe technology. It's very standardized, as pretty much everybody in here knows. The main thing you need to read from a disk device is a block I/O protocol. So there was an added one for NVMe access. And similar to how there's a block I/O capability to talk to the disk, there's a way to specifically talk to the controller firmware or the disk itself, which is through these pass-through protocols that are defined in the specification. So being able to boot from the disk is useful, but there's a number of other features that hard drives traditionally have that NVMe also has access to, but many people look at NVMe as just a quick boot media. They don't look at it as a traditional hard drive. So traditional other disks like IDE disks, SATA disks, they had many features that we implemented in firmware, but in many cases with NVMe, since it came out at the time it did, and since it was so fast, we may have overlooked. There's also a number of additional features that NVMe offers that are mainly used only at the OS timeframe. And we can also use these in the firmware space to give more advanced capabilities to the users. So just to note, these are not missing from the specification. The specification provides the full functionality for you to implement it. They just may not be in everybody's implementation, and you can build on top of the blocks, as we're going to talk about in a minute, to implement these features that we're discussing here. So some traditional hard drive features that are missing in the traditional UEFI. SAT3 password support. This is where your hard drive has a password, so as you're booting up, you need to enter the password to unlock the drive, or it doesn't boot, or basically you can't access it. Pyrite support. This was something added on SATA drives as well. They were Opal drives, where there's some self-encrypting capabilities of the drive. You can encrypt certain sectors so that some part is open, but most of it's encrypted. And then block SID support. This is a specification that governs, it's actually from TCG, how to handle a self-encrypting drive where the OS wants to take ownership of the drive and start the encryption process. So these are also some of the additional features NVMe offers that are new that we can make use of in UEFI as well. NVMe namespace creation. Basically, an NVMe namespace, for those who don't know, is where you can basically section up the drive and it will appear as two different drives to the system. This can allow you greater throughput when you're writing to almost two different partitions, but it's a greater power than a partition because it's actually looked at as two different drives. Controller firmware update. The specification provided a generic way to update the firmware controller. And as we've talked about here many times, the security behind UEFI, we've got capsules. So we want to use the capsule method to update the controllers in a generic way. And the last one there is NVMe Metadata. This is where NVMe drives have a separate section of them to store metadata that can be used for hashing or CRCing of the information on the drive so that every write gets an additional write to this section to make sure data integrity is there. So when you read it back, you can verify the integrity on the way back. So, like we were talking about before, using these interfaces in UEFI, how is somebody supposed to add these features if they're lacking in their platform? So UEFI provides those building blocks. The main one here is the pass-through protocol. And as we're going to talk about at the end, these pass-through protocols exist for most devices that we interface with today. So you can look at other pass-through protocols in the specification to provide features on top of other hardware that's there as well. You're basically able to talk directly to the driver controller. And like I said, using this, we're going to implement these features as long as the NVMe drive provides support. Of course, a drive vendor may lack support of metadata, for example, so you couldn't apply this there. SAT3 password. It's the standard method that we all know where you can marry a drive to a platform. You can have a password that's entered by the user. If somebody walks into your facility and steals that drive and walks out with it, it's going to be unusable unless they knew the password correctly. Even if the drive has no password set, the right thing for the firmware to do is to freeze lock the drive. And you're going to hear that term used a lot throughout the rest of this presentation. When you freeze lock a drive, it pretty much prevents all of these features being applied at a later time. So you can't set a password later. This is because if you had not freeze locked the drive properly, some malicious program that has gotten control in the operating system could set a drive password on your drive, and then it becomes unusable. So you want to make sure, in all of these cases, you'll hear it, you want to make sure that you're freeze locking the drive accordingly. So how are you going to implement SAT3 password? So if the password's currently set on the drive, if you have a standard password that you're using across one device class, for example, you wouldn't have to prompt for the password, but normally you would prompt the user for the password. And then you provide the password to the drive using the pass-through protocol to send the proper SPC4 command to unlock the drive. Basically, you'll pass that password on through the SPC4 command. If the password's not set, you can use the NVMe pass-through protocol to send the proper SPC4 command to freeze lock the drive so that a password cannot be set at a later time. Now, it's important to also note this EFI security storage protocol. It's an optional protocol, but it does provide an alternative method to do SPC4 commands. The pass-through protocol takes in a port that you're going to be reading to or writing from. The security protocol already knows those ports, so it abstracts that from you, so you can use this protocol instead. Next was Pyrite support. This is the self-encrypting drive data. So it protects drive data by encrypting data on the disk itself. The drive can do whatever it wants for the encryption of where it can have certain LBA sectors unlocked so that the initial bootloader can be there. And then it can unlock itself as it boots later. But in the case of firmware, you would probably encrypt the entire disk and then prompt for a password before unlocking the drive itself entirely. So to do this, we're once again going to use the NVMe pass-through protocol. You want to then take ownership of the storage device by setting a new password to the CPIN credential. And this is all coming from that NVMe specification. If you're going to look for additional details, it's there. Then you want to activate the locking service provider, or SP. You then want to change the admin 1-pin locking service provider. And you can also set an additional user password if you want, but you need to at least set the admin password. And then you want to configure the locking objects, or LBA range. This is where you're saying what regions of the drive should go into the self-encrypting area and which ones would remain unencrypted. And like I said, the entire disk is an option if you want to do that. But once you've done this, on subsequent boots, the password must be supplied to unlock the drive. Otherwise, you're never going to be able to get to the data again. This differs from SAT3 password in the case of where the drive actually doesn't have it encrypted in SAT3 password. It's just, it won't respond to commands and read data off the disk. In this case, even if you cracked open the drive and tried to get access to it, the data is encrypted directly on the drive, and it's decrypted as it's read off the disk by the cryptographic engine on the drive. So block SID one, like I said, this is coming from the TCG specification. This is kind of a dance between Windows, or Linux for that matter, and the firmware. Because Windows might want to take, or Linux again, the operating system I'll call it, sorry, might want to take ownership of the drive and do the encryption on the drive itself, so that the initial bootloader is unlocked, but then everything else on the media, it will unlock as it authenticates the user. But the problem is, we're going to be freeze locking the drive normally. And if we freeze lock the drive, the operating system can't go ahead and take ownership of it and do anything at that point, because all those settings that it wants to set are unsettable at that point. So what the OS normally wants to do is it's going to follow this specification to request the firmware, hey, next time we're booting, check to make sure somebody's at the machine. And once physical presence is verified, similar to a lot of TCG physical presence checks, and you'll see that when we talk about, or if you look at the specification at all, they call it the physical presence interface, or PPI. It has nothing to do with our traditional PPIs that we would look at in our specifications. But once you verify the physical presence check, we would then leave the drive unlocked, allow the operating system to take ownership of the drive, and do whatever encryption it's looking to do at that time. Secondly, block SID support can be detected using level 0 discovery command with feature code 0402. A technical note there, but all it's really saying is that you should inform the operating system if you have any drives that have block SID support, because the operating system would never request to do one of these operations if it didn't know one of the drives had the capability. So you should note the drive to the operating system. So sample implementation again. On every reboot, the OS would send a mailbox event. So if no mailbox event has occurred, like a normal boot, use the pass-through protocol to freeze lock the drive. And you can refer to the TCG storage specification for the proper command information in the table marked block SID authentication channel. It was a lot of bits and it wouldn't have done very well on the slide, so it's better just to tell you to refer to the spec. But if a mailbox event has occurred, check user presence, some sort of pop-up to make sure that, hey, we've requested some sort of change based from your operating system. Is this something you've done? So that the user can know that some sort of request has been made. and then continue to boot normally without freeze locking the drive. Where in the first example, we would have freeze locked the drive. Or we did, sorry, using the pass-through protocol to freeze lock the drive. Multiple namespaces. This is that one again where we're segmenting the drive almost into two different drives on the same controller. It's a good way to utilize the storage media so you can be writing to both locations at the same time. Most operating systems today support multiple namespaces. But the problem is that what happens if I want to set up my multiple namespaces before I even install an operating system? I want to install one version of Windows here and one version of Linux there. And if I can't do that until I'm installed or I've loaded an OS level driver, it can get complicated. So you can move this support into the firmware space so that you can take advantage of it there. And this one, compared to some of the other ones, is more of a user interface interaction more than anything else. The more complicated part is providing them the proper setup menus to view the namespaces, create new ones, delete them. It's more of a UI aspect. But then when you're doing the actual functional implementation of it, you use the NVMe pass-through protocol to use the attachment management commands. These are both found in the NVMe specification that we talked about at the beginning of the presentation. They're pretty straightforward, but you use those to manage the different namespaces on the drive. The good thing is, though, is that any EDK2 or drive NVMe support or block I/O will install a number of them for however many namespaces there are. So even if you don't have the namespace support for creation in your firmware, the firmware would automatically support any additional namespaces that are created from the OS timeframe too. So there's no change needed in the block I/O capabilities. The next one was the controller firmware update. So updating a firmware should be done in a safe and secure manner. I'm pretty sure we've heard that in about 6 or 7 presentations this week alone, let alone over the past 2 years. So if you're going to use the pass-through protocol and capsule, you can do this in a secure manner. And it provides a standardized method to push the firmware to NVMe devices. Once again, this is another one of those mailbox events of where we've got a capsule that needs processing on a reboot. So if there's no capsule, continue booting. If there is a capsule, verify or authenticate the capsule. Push the capsule to the drive using the NVMe pass-through protocol via the image or firmware image download command and the firmware image or firmware commit commands, and then reboot the system so that the new firmware can take effect on the drive. Okay, I know it's been technical. This is the last one, I apologize. NVMe Metadata, this is where you can use the metadata which is written to an extra portion of a drive to verify integrity of the information stored there. So when data is written, the metadata storage will use the proper CRC information for verification, and on read, it can be your responsibility to get the information. So the first thing is the drive must be formatted correctly to accommodate metadata. It's something that's done when you're formatting an NVMe drive. Once metadata is enabled on the drive, basically your standard block I/O will not work on its own. The block I/O is going to be passing buffers of the length of what you're trying to read and write from the drive, which metadata is an additional addendum to the read and write data. So you'll need to modify the underlying block I/O implementation to use the pass-through protocol with an additional section of data tagged on to your block I/O buffer that you were trying to get. So if I'm trying to get 512 bytes from the drive, the block I/O will take the 512 in, but when it uses pass-through, it's actually going to pass in like 538 or some additional buffer length to get the additional data from it. Now, ironically, on a write, when you're writing the data, the drive will traditionally do whatever its CRC information it's trying to do is. You actually can pass in all zeros for that additional buffer, and it will still accomplish it correctly. But on a read, you probably should take a look at the data to make sure it matches the integrity of the block that you were trying to read, so that you can match it up. And if it fails, return some sort of error. Otherwise, return the data back and return success. So, some brief conclusions. NVMe is relatively new. We've only had it around for less than a decade at this point, but it really is very pervasive in the industry. It came out and it became the most popular media within a couple years. It was quickly and broadly adopted, basically. And UEFI provides these building blocks to expand on the technology that is in the base specification to do something more advanced through these pass-through protocols. And that's just a note to take a look at what other pass-through protocols exist for what other media is out there, and how can we expand and provide more advanced features to our customers so that they can better utilize their systems. And that's it. So, questions?
Yep, one on the far side of the room. I will go take the microphone to him.
So when I was doing a little bit of work with NVMe drives, I got the feeling that a lot of the commands that I was submitting were essentially SCSI commands or extended SCSI commands that got passed through the pass-through protocol. And I'm wondering, was it really necessary to have an NVMe specific pass-through protocol instead of just using the SCSI pass-through protocol?
You're saying from a spec point of view?
Yeah, I'm just asking. I mean, is it actually SCSI at that lower level with some extensions, or is it completely different from SCSI?
SCSI with a header that says which device it's going to.
Yeah.
Right.
Yeah, for those who didn't hear the question, it's just SCSI that says what device it's going to in the header.
Yeah.
And there were legitimate reasons back in the day. I mean, it's historical at this point. There are some things that, you know, just are SCSI-ish, but not SCSI enough that you had to have a different NVMe header for the pass-through protocol.
Yeah.
I know that's not SCSI enough, that came out wrong, but
Yeah.
you kind of get the context.
Yeah.
It's an unfortunate acronym. We should stop having those in this industry.
Additional questions?
Yeah.
Okay.
All right. Well, that was the last session. Thank you very much, Zach.
Thank you, guys.